sorry. Okay. All right. So, anyways, the whole activity, which it goes by the name TTbar Deformations, and roughly speaking, this is a class of deformations of two-dimensional quantum field theory. I will always talk about two-dimensional quantum field theory, and so these are special deformations which are generated by irrelevant in the renormalization group sense operators. Usually, conventionally, such irrelevant operators are, I mean, usually are not conventionally are not considered as a good deformations because they generate non-renormalizable perturbation theory with all that infinite amount of necessary counter terms and a bad, poor control of the short distance behavior, and so these theories are, if not inconsistent, are not very well defined. But there is a certain the whole thing is that there is a special class of such deformations, renormalization group irrelevant operators with such properties that the deformed theories have robust properties and even solvable in certain sense. Now, my motivation for this study is generated by the attempt to understand the space of quantum field theories, sometimes called theory space, in geometrical terms. I will use notation sigma, this letter here, for this space of quantum field theory. So very roughly speaking, the space of theories all right, so that's what I was starting to say, that the space of field theories is once there is a feeling that it has interesting geometric structure, which is still to be most of it is still to be discovered. And interesting part about it is that if you try to do that, there is again a feeling that you need to extend the notion of quantum field, local quantum field theory, in order to make this associated geometric structure natural. So if I just start with the quantum field theories in usual Wilsonian sense, and then in order to give it a natural geometric structure, I need to attach additional theories, include additional theories which are not local quantum field theories in the Wilsonian sense. So I will here I will discuss certain deformations, which, as I said, which are the TTbar deformations, and these deformations, I hope, will help me to understand the geometry of the associated the true geometry of the space. All right. So, of course, there are other angles of interest to the subject, which I mostly not going to discuss in any details, and I just list them here with one after another. Some of these subjects, some of these angles I will mention in the course of the talk, but mostly I will be concentrating just on the on the role of the TTbar deformations in the space of two-dimensional quantum field theories. All right. So if one wants to have a broader look at the subject, I recommend very nice review, which is quoted here. All right. So so let me just say a few words about what geometric notions we know we have in the space of quantum field theories, and one of the most important one is the renormalization group. Now, generally, the renormalization group, of course, is the way how scale-dependent scale transformations are represented in the space of in the quantum field theory, and I will discuss it in terms of Wilson's renormalization group. I don't think I need it. This is so kind of everyday tool in theoretical physics today. So I don't think I need to say much about how Wilson's approach is defined, but basically in one of the ways to look at it, the sigma, the space of quantum field theories, is realized as a space of quasi-local functionals. So if you have a collection of fundamental fields, which I denote capital phi here, then the space consists of actions which are integrals of local densities, which depend on phi and its derivatives. So in general, any number of derivatives may be included here, but it's in addition, it's assumed that the theory is equipped with the ultraviolet cutoff, and this functional is quasi-local, meaning that its derivative expansion converges for field configurations which have wave vectors not much larger than the cutoff parameter. All right. So of course, I mean how this represents the scale transformation is that if you just simply rescale the coordinates, this also changes the value of the cutoff parameter, and in order to return it back to original value, one needs to integrate out the modes of the field phi, the fast modes with the wavelengths between basically to return the value of the cutoff parameter to the original, to return the cutoff parameter to the original value. Okay. So this renormalization group transformation generates a flow in the space of field theories defined this way, and I will symbolically use this notation, which of course is in some coordinates or a collection of coupling constants, is just a collection of standard renormalization group equations with this b standing for the beta function, minus beta function actually. All right, so this is the way how the renormalization group transformation acts, but the Wilsonian idea of quantum field theory is usually based is generally based on the presence of the fixed points. So if you have a fixed point which is defined in usual way, then it's stationary under the renormalization group flow. Then it generates then the Wilsonian quantum field theories are associated with the renormalization group trajectories which originate at large negative L. L is a logarithm of the length scale, originated at some flows from some fixed point. So in general, the pattern of flow renormalization group uh, between different fixed points may be complicated, but generally the Wilsonian quantum field theory is a trajectory which eventually could be traced down to some fixed point. So that's the collection of such field theories constitute conventional Wilsonian quantum field theory in I think in contemporary understanding. Okay, and now another geometric notion which I will use, and that's important part, is the tangent space. And the tangent space, it's natural to associate the tangent space with the space of local fields. In this formulation, local fields are just certain expressions, local composite fields built from phi and its derivatives, any number of derivatives localized at a given point x. And of course, this kind of expressions form a vector space, because if you add, you can add such fields and remain within the same class. And so I will use the notion of the I will denote f sub qft the space, the vector space of the local fields. Okay, this of course this is has a, in quantum field theory this has a structure like correlation functions, or in more compact notations operator product expansions, or algebra of operator product expansion, which incorporates most important properties of the correlation functions. And so in addition, that I will use is that among the fields there is a local energy momentum tensor, which is symmetric and is conserved, and this is the way for the theory to enjoy the rotational and Lorentz and rotational and translation symmetry. So anyways, it seems natural to identify the space of local fields with the tangent space to the tangent space to the space of field theories. And this is because any small deformation of the field theory is amounts to adding a collection of local fields. So so this is a any local field is a tangent vector in this deformation. In fact, there is a little bit of qualification, because if you add the total derivatives to the action, it doesn't change the bulk properties of the theory. And also, if you want to insist on the Lorentz invariance of the theory, you want to keep your only scalar fields as the generating deformation. So in fact, what is to be identified with the tangent space is the factor space of f over derivatives and the subspace of scalar fields. But that's not very important qualification. One can consider a more general situation, and it's actually interesting to consider a more general situation that I'm not going to expand on that. All right. So anyways, this identification will allow to transfer the structures of the space of local field into geometric notions in the space of field theories. But there is one small problem. It's not actually small, but in fact a large problem, which is a short distance problem, and sometimes referred to as ultraviolet completeness problem. Very roughly speaking, from mathematical point of view, it's the problem of what kind of singularities are admissible in the functions which describe operator product expansion. So but what I want to emphasize is that if we want to make the space of theories into a geometric object along the lines which I mentioned before, with the tangent space and everything, it's not sufficient to have only Wilsonian field theories. So one needs to add some other objects, some field theories which are not described in a conventional way, in order to have a consistent geometry. That's the. It's not. It's just a feeling, and I'm still describing motivation for this study. All right. So let me. Let me mention that's of course well understood that if you take a space of field theory sigma as a collection of quasi-local actions, then majority of the theories are not represented as Wilsonian theories. Roughly speaking, if you take a renormalization group flow and try to integrate it backwards in the renormalization group time to shorter distances, it eventually it's not, in general it wouldn't converge to any fixed point, but instead it would leave. So if you try to integrate it backward, it would leave the space sigma, which is and go to something beyond this space, and so basically the points outside, basically the points outside this kind of picture which I drawn here is kind of assumes that the space sigma has a boundary, and so there is something which lays beyond this boundary, which is not clear what it is, generally speaking, but definitely the points outside are not correspond to theories which cannot be represented by convergent functional integrals like this. And so again, as I said, it's very tempting to think that a large, in fact, some part of this expands beyond the standard definition of theories should be included into geometry of this object. All right. So that's again motivation, and so I tried to explain why I concentrated on that. So let me come to the and again, if you have this geometric object, studying various flows in it, of course, is very useful in order to explore its structure, and that's why I will be discussing the TTbar flows. All right, so let me just start with very simple exercise, which is at the heart of all this TTbar and generalized TTbar deformations. If you have, suppose you have two local currents, two local fields J, which are vectors, and they are conserved currents. That means they have zero divergences. And let's consider two different currents like that, and form the bilocal combination, which is shown here, which is one current wedge product to another current. And so this is a bilocal object E mu nu is a unit antisymmetric tensor, and it has this product has a number of remarkable properties which depend only on the conservation of the currents. So to see that, let's take a derivative with respect to one of the coordinates x here, d over dx lambda, and apply the identity, which is the cycle symmetry of the products like this is identically zero. That's because any totally antisymmetric object tensor in 2 dimensions is identically vanishes. So if I apply this thing here, okay, to this object over here, and use the conservation of the currents, I arrive at the identity that the derivative of this local project over one of the coordinates is expressed in terms of the sum of the derivatives over x and over x prime. And that means that if I use operator product expansions like this, operator product expansions for the combination appearing in the right hand side, this whole combination would consist of solely of what I call derivative terms. And derivative terms is just a combination of fields with the C number coefficients with the which are completely composed of the total derivatives. So the derivative of JAB over any of the coordinates completely consists of the derivative terms, and that means that JAB itself has very peculiar structure. It has a it can involve any number of derivative terms, but it could also involve a non-derivative term. But the coefficient operator product expansion, the coefficients of the operator product expansion in front of this thing is going to be a constant and dependent on x. Okay, and so that's the only non-derivative term, and in interesting cases, it's non-zero, it's non-trivial field. It has a number of remarkable properties which follow just from the definition of this thing. Let me just mention a few very obvious properties. So that's what I repeat. Again, I must say that this elegant derivation is borrowed from John Cardy. But there are several nice properties which this field defined this way is by the way, this field is defined as we see is defined uniquely given two currents. It's defined uniquely modular derivative terms. So up to adding derivative terms, it gives unique definition. And because it's unique definition, it also has some very robust properties. One is that the dimension of this field is just the sum of the dimensions of constituent currents. And what is even more interestingly is that expectation value of this field over any translation in the invariant state, I will come back to it earlier, factorizes in terms of expectation values of currents themselves. This is because if I take this equation over here, that JAB, the bilocal itself, is this field x plus derivatives, and I take expectation value of this object over translation and invariant states, of course, derivative terms drop out, and I have a expectation value of this field equal to expectation value of this bilocal product. And remember, this bilocal product consists of currents, and it's bilocal, but the expectation value doesn't depend on the separation of doesn't depend on the coordinates and the x and x prime. So we can take a limit of the separation, large separation, in which case this expectation value splits into the factors expectation values of the current. So this is very general structure, which depends only on the conservation of the currents. And I must say that I must add, which will be important, is that although I spoke in terms of expectation values, vacuum expectation values, it's actually remains valid for any translationally invariant state. So if you replace the vacuum expectation value by a diagonal matrix element between stationary states, this factorization property will remain valid. So this property with the expectation value replaced by a diagonal matrix element is still there. All right. Okay. So the definition of the field X, defined this way, gives actually a definition of for every field theory regarded here as a point in the space sigma, gives a definition of the tangent vector on the vector in the tangent space. And so this generates a vector field on the space sigma, and consequently it generates a flow. Every pair of conserved currents can be used to generate a flow in the space defined by this equation, provided that deformation with the field XAB doesn't break conservation of the currents which are needed to construct this field XAB. This is a formal definition that the flow is generated at each point along the curve parameterized by flow. Basically, it's a curve parameterized by a parameter alpha, and at each point, the tangent vector is the field XAB built in terms of the field theory associated with the point alpha along the curve. All right, so that's general construction, and it can be used to build a number of interesting examples of such flows. But I will consider two examples. One is the primordial example, and I refer to it as a TTbar proper, in which this is the theory in which these two currents, JA and JB, are just the appropriate components of the energy momentum tensor. So a remarkable, very nice feature about this TTbar proper deformation is that it exists for any arbitrary quantum field theory as long as it has a conserved energy momentum tensor, which is pretty general for the general feature of the local field theories. So once you have that, you can take these components, or much rather, these are Cartesian components, but it's convenient to change to light coordinates, or in Euclidean language, these are complex coordinates in the two-dimensional space, and then use the same construction and define the field, which I will refer to as a TTbar, and it just happens to be built according to the same prescription from the components of the energy momentum tensor. Here, T is ZZ component, T bar is this is a standard notations, but this expression is the reason why this object, not the reason, but I mean, historically, it's the source of the name TTbar for this object. Okay, so we see that in any field theory, we can generate a flow with the help of this operator, and that generates deformation, which has remarkable properties. One of the properties relates to the expectation value of the this TTbar operator, which I will consider in the case when my two-dimensional space-time geometry is a cylinder with one of the coordinates, spatial coordinates, compactified on a circle. And so in this situation, it's natural to assume that the spectrum of energy momentum spectrum is discrete, and I will denote n the eigenstates. And so the factorization property of the composite TTbar operator like this is expressed by this relation, which expresses its expectation value through expectation values of the components. And this is special case in which we are dealing with the expectation values of the components of energy momentum tensor, which are expressed in terms, of course, in terms of energy density, momentum density, and spatial stress. And as a result, this kind of expectation value is explicitly expressed in terms of the finite size energy levels of the system. That's the main equation which is going to be used, because now I'm going to use this field TTbar to generate TTbar flow, what I call TTbar flow according to this equation. And this pi is not okay. All right, never mind. So this is the TTbar flow, the flow generated by the vector field TTbar, and it has some, just like I said, it has some remarkable properties. For example, one of the examples is that you could write down closed equation for the flow of the energy levels, which I denote E sub n, which depend on R, energy levels in this finite size geometry, is a function of R, and alpha, the coupling the deformation parameter. And because of the factorization property, it's not difficult to it's possible to express it in terms of energy levels themselves, and then the energies, deformed energies, satisfy this equation, which happens to coincide with Invis's Burger's equation with some sort of driving terms, which depends on the momentum of the state. This makes the deformation solvable in certain sense, meaning that if you have energy levels, finite size energy levels of undeformed theory, and use them as initial condition for this equation, regard this alpha as some sort of time, you can uniquely integrate it and obtain the spectrum of the deformed theory. And it's something which is instructive to do. Okay. And just here, the equation itself doesn't depend on which level we're talking about, so I drop the index n in the notations. So that's the deformation of the finite size energy spectrum, and also it's another exact result which can be derived various ways. Is the deformation of the the deformation of the S matrix, basically. Here I demonstrate how the elastic two particle S matrix is deformed. It just gets additional phase, scattering phase over here. which is written here in terms of the rapidity difference of the particles, uh, and so this is very explicit and simple deformation of the modification deformation of the scattering amplitude. The only thing which I want to stress now, mention here, is that it has a abnormally fast behavior at large energies. So depending on the sign of alpha, the scattering phase either grows or grows towards negative values very fast with the energy of the particles involved in the scattering. In writing this thing, I assume that there is only one sort of particles with the mass m, and in the future, in what follows, I will set m equals to 1. This is just for two particles matrix, but in fact this deformation of this matrix can be brought up to very nicely brought up to the deformation of the whole full S matrix. This was due to Dubovsky, Gorbenko, and Mir-Baibai a few years ago, and that's actually was based on the proposed relation to Joukov-Teitelbaum gravity, because there is some tantalizing relation of the whole business with some models of quantum gravity, and so this relation first, there are two things. One is that there is a generalization of this deformation which allows one to write down explicitly the deformation of the full S matrix, and also it supports the idea of the relation to the quantum gravity. I'm not going to expand much on that, but I will come back to the deformation of the S matrix. All right. Let me just. I have to move fast. Let me just say a few words about the deformation of the energies, and I will concentrate attention on the ground state energy, which corresponds to the momentum equal to 0. And that, in this case, the deformation equation, the Burger's equation, admits very explicit and simple solution, which can be understood as follows: if you regard alpha as a parameter and consider E as a function of R, it's actually a good idea to consider inverse functions. R of E, which can be R alpha of E for the deformed theory and R naught of E for the original theory. And then this equation basically says that inverse functions are related in a very simple way, which in fact says that if I look at the plot of the function of the deformed function R of E and R alpha of I, these plots are related by simple affine transformation, and this also applies to the functions E alpha and E naught. You just make a affine transformation of the coordinate axis in the so it's actually allows one to see what happens to the ground state energy very easily. So suppose I'm starting with the conventional Wilsonian quantum field theory, and that's how generally the ground state energy behaves. In that case, the large R, it's dominated by the bulk energy density, vacuum energy density, and at short distances it's saturated by Casimir force, because short distances in standard Wilsonian field theory is controlled by a fixed point or conformal field theory. therefore generating a Casimir behavior. But now if I apply this thing, that means that what I only need to do in order to look at the deformed plot of the deformed ground state energy, I just need to make a fine transformation of the coordinate axis, and depending on the sign of alpha, I have two possible patterns. I have two possible patterns. This is for the left-hand side is for positive alpha, and this is for negative alpha. In fact, both of these pictures indicate that the resulting theory cannot be conventional Wilsonian quantum field theory. For example, in the case of positive alpha, the ground state energy just doesn't have any singularity at small distances, which is hardly compatible with the idea of the field theory as a collection of local degrees of freedom. On the other hand, if I look at the negative values of alpha, instead the ground state energy develops a singularity, square root algebraic singularity at finite distances, and so both kind of behavior are not typical for conventional quantum field theory. So some generalization, some way outside the definition of quantum field theory, some extension of the notion of local field theory is needed in order to incorporate this sort of behavior. In fact, the behavior at alpha positive is yeah, it probably calls for some sort of relation to quantum gravity, but I'm not going to expand about that because there is a question about overall stability of the ground state in this. I'm not going to discuss it, but there is a question about the overall stability of the ground state in this regime. So I will mostly concentrate on the case of negative alpha, where this is the singularity which appears here is similar to the Hagedorn singularity in the string theory. All right, and I will refer to this regime as a Hagedorn regime in the deformed theory. All right. So here I just want to skip it. It's just a explicit form of the deformed energy. In the case when the original theory is a conformal field theory, there is explicitly this singularity, which singularity at finite r, which is incorporated in the square root. But let me just remind you that the Hagedorn singularity and all this is related to the behavior of the density of states. This is well understood. Basically, the one thing is to remember, of course, is that the ground state energy, in this finite size geometry, which I discussed here, incorporates in itself density of states in the system with large spatial size, and this is because the partition function, which is of the theory on this on the geometry of this cylinder with one coordinate compactified and the assuming that the cylinder is long, it's on one hand, it's dominated by the ground state energy in the picture where the coordinate y along the cylinder is taken to be the time, the Euclidean time. But one can take another picture in which the coordinate x around the cylinder is taking playing a role of Matsubara time, and y is instead a spatial coordinate. So the system now is spatially very large or infinite, but the imaginary time is compactified to create a Matsubara representation of the quantum field theory at finite temperature. And this gives a relation between this ground state energy and the free energy of a free energy density F of the theory in the large spatial size, but at finite temperature related to the parameter R. That's usual Matsubara representation. And of course, given this relation to free energy, one can restore the entropy, which is related to the density of states, according to usual definition. And so basically the entropy is extensive quantity. So it's controlled by entropy densities, which I denote sigma here, and which depends on the energy density of internal energy density, and that relates as usual. It's related to the free energy by Legendre transform, and so one can recover the energy density from energy density in thermal state from the ground state energy. And for example, if we are talking, if we have a conventional quantum field theory, which is whose short distance behavior is controlled by a fixed point, then the Casimir behavior of the ground state energy translates into the standard formula, which says that the entropy is proportional to the square root of the energy density. This is celebrated Cardy formula, which shows how the density of states grows as e to the square root of energy density in a conventional quantum field theory. On the other hand, I can try to compute the same thing in the TTbar deformed, and here the deformed theory, and here I produce the result for the TTbar deformed conformal field theory. That's just the result, and we see that of course the at large energy densities, this square root produces behavior which is linear in epsilon. And first of all, the equation makes sense for any epsilon if alpha is negative. In this case, the behavior at large energy densities is linear, and so the density of states grows like exponential of the energy, which is exactly the Hagedorn behavior characteristic for string theories. I just note in passing that I could formally repeat the same analysis for positive values of alpha, and it would show that formally it would suggest that the range in which the energy density is allowed to be is limited to epsilons below a certain value controlled by the parameter alpha. So in some sense, this equation would suggest that the theory emerging this way has a limitation on possible energy densities in this spatially large system, and that's would be very interesting to understand how it's interpreted. I at the moment I don't have very good idea, and that's very intriguing, in fact. All right, so let me move forward. I'm almost out of time, so I just say a few words that this very large, very fast growth of the density of states one might think that it's related to the growth of the behavior of the scattering phase, which grows very fast with the energy. But it turns out that in fact there are generalization or extension of the TTbar deformations, which do not have this fast behavior of the scattering phase, but nonetheless develop a Hagedorn behavior. And this is something which happens which is very general situation in integrable quantum field theories. As I mentioned, the TTbar deformations appear every time when you have a pair of conserved currents, and integrable quantum field theories have enormous, infinitely many conserved currents. So you could in fact construct a whole family of the TTbar-like operators, which I denote here. TTbar with the index S. It depends on the how the collection of local integrals of motion is structured in the theory. But anyway, because there are infinitely many of such integral conserved currents, there are infinitely many deformations, and it's possible to show that such deformations preserve the integrability. So one could generate a flow, this time the flow with infinite parameter family. The parameters are denoted alpha, which are generated by these operators, and again, these deformations have nice properties, and it's convenient to discuss these deformations in terms of the S matrix, the S matrix of the theory. Namely, because we are dealing with the integrable field theories, the theories of this kind, they have a very rigid structure for this particle scattering, leading to the so-called factorizable S matrix, in which only elastic processes are allowed, and as a result, its kinematical consequence, the full S matrix factorizes in terms of two particle S matrices, and the two particle S matrices, well, I mean, they satisfy a number of conditions, including unitarity and crossing and analyticity, and certain bootstrap equation, and certain Young-Baxter equation in more complicated case. But that's not important. What is important is that for my analysis is that imposing these conditions leave a freedom of adding a factor to the two particle S matrix, which is referred to as a Cdd factor. That's a factor which depends on theta, on the energy of scattering particles, and satisfies some simple relations. In particular, it's periodic function of theta, and therefore so that's basically a general way, given a collection of particles, that's adding the Cdd factor is general way of deforming the S matrix itself. And it turns out that this deformation, Cdd deformation of the S matrix is directly related to this deformation of this infinite parameter family of deformations generated by the operators TTbar sub S. And so the Cdd factor, which appears after under this deformation, is just exponential of the is exponential of the sine theta in growing power. So there is a sum of the terms, and so what I'm saying is that infinitesimal CDD deformations of this matrix is the same in this language as the TTbar generalized TTbar deformation of integrable quantum field theory. All right, so if I look at this equation, it looks like it has even worse high energy behavior because there are higher powers of higher exponentials of theta. These are higher powers of center of mass energy, but this, of course, this is not necessarily convergent in the whole theta plane. So in fact, general CDD factor, the way the analytic this has the series generally converges in a finite part of the theta plane, and its analytic continuation could develop poles. So general structure of CDD factor is involves a pole part which absorbs the poles in the finite part of the rapidity plane, and there might be an additional factor where the sum with some parameters which decay very fast with S in such a way that the sum here converges at all theta and generate entire function of theta. So so that's most general way to describe the CDD factor, and that this kind of CDD factor covers the whole space, the whole flow, infinite dimensional flow, infinite parameter flow generated by this deformations, TTbar sub S deformations in the integrable field theories. All right, so we can start studying that, and it's actually interesting to know that there is this class of CDD factors which have quite decent behavior at infinity. You just drop this exponential and limit attention to the pole, to the collection of certain number of poles, which can be infinite, but it doesn't matter much. But generally, in the case of finitely many poles, this factor has quite decent behavior at infinity, and one can try to understand the consequences of the scattering theory. In fact, it's not. There is a universal technique in the integrable field theories, which allows one to use the S matrix and restore the density of states or ground state energy using the so-called thermodynamic Bethe ansatz. That is related to the same statement that the density of states is controlled in density of states in the spatially large system is controlled by the scattering matrix. And so if one add the density of 2 particle, 3 particle, and multi-particle states and sum this up, and one can recover the full density of states. Mathematically, the technique is known as the thermodynamic Bethe ansatz approach, and in fact, it can be regarded as a sort of device which is a black box with the input of the S matrix and output the ground state energy. This is the form, symbolic form of the thermodynamic Bethe ansatz equation. It returns the ground state energy, or which is the same, the free energy in the a spatially infinite system at finite temperature, and the functional epsilon, which is related to the density of particles in the thermal equilibrium state, satisfies this nonlinear integral equation with the kernel, which of course is the derivative of the scattering phase, which is natural because it's the derivative of the scattering phase, which controls the density of states. Okay. Usually, these equations admit numerical solution, which is usually obtained by iterating this equation. You start with the free particle part of this density, and then substitute it here and start iterating. And this can be done for any kernel, and actually it was studied for the how this Cdd factor modifies the kernel, and so how this Cdd factor affects the affects the result is a interesting question, which was addressed. I think it wasn't systematically addressed before, but there is some experience with that, which basically shows that if you take this iterative solution, the iteration with generic Cdd factor of this type, and with the finitely many Cdd factors, what happens generally is that iterative solution converges at sufficiently large R, but with generic Cdd factor, without with generic position of the additional Cdd poles, the poles are associated with resonance states, but with generic parameters B, the iterative solution breaks down, and the iteration stop converge at sufficiently small R. And in fact, careful analysis shows that the computed ground state energy develops some sort of singularity, which looks very much like algebraic square root singularity. And so this shows that the situation here is also the Hagedorn type, which is now not related to the behavior of the scattering phase, to particle scattering phase at infinity, but rather a collective phenomenon of including the multi-particle states. I might say a few words later about what happens, but that's the experience. And what I want to use remaining minus 10 minutes of my talk is to sort of mention some different approach, which general there is a mathematical technique which makes it more efficient, the solving of this kind of integral equation, which is thermodynamic Bethe ansatz equation, which goes by the name pseudo arc length continuation, and it happens to work very nice. And what I'm going to produce is the result of the forthcoming work by Gian Camillo, Tiago Flori, Matt Lenses, and Stefano Negra and myself, where we applied it to a class of Cdd deformations. I will produce results for what I call what we call 2CDD model, which is just a deformation of the S matrix of free particles with Cdd factor, which carries just one resonance whose energy and width is controlled by two parameters, theta naught and gamma. So if you do that, you use this technique, you produce the behavior of the ground state energy, which is the red branch is the iterative solution, but there is another solution of the same integral equation, which is the second branch, the blue branch. Two branches merge at certain Hagedorn-like temperatures, Hagedorn-like x. So this is qualitatively the same as in the TTbar proper case, the same behavior as the TTbar proper case. Here is the how the densities of particles behave in this solution. But what I want to stress is that the second branch, which is not accessible by iterative solution, the iterations wouldn't converge to this branch. It also at large distances it also develops a linear behavior. So it looks like it's another vacuum in there is another ground state of the theory, which is actually energetically lower than the iterative solution, but nonetheless it looks very peculiar, because normally in such situation one would expect the decay of the upper vacuum into the decay into the lower vacuum, which doesn't happen. And similar situation, of course, is similar remark applies to TTbar proper. This is another value of the parameters, but you can see that the situation is the same. So that's basically confirms that the singularity and the nature of the, first of all, there is a Hagedorn singularity. The nature of the singularity is the same as in the TTbar proper square root, which is also very strange, because if we have a kind of, if we think of this singularity as a transition from one branch to another, one would generally expect well, if one think of it as a sort of phase transition, one would expect a more complicated singularity, and this one still remains to be of the simple algebraic form. So it's still not clarifying what is going on, but at least showing that this phenomenon is very general, and so that's basically. So that's more or less all I wanted to report now. I'm not going to give a conclusion, because I don't like conclusions. Well, I like conclusions, but I very seldom come to conclusions. And as here I just mentioned several open questions related to this. So let me stop at this.
Well, thank you very much, Sasha, for that beautiful talk. First of all, let's unmute and thank Sasha. Okay, so let's open it up to questions. Just feel free to unmute yourself and ask. If you don't,
I have a question. Sasha, it's Steve Schenker. It's nice to see you.
Hi, Steve.
Thanks
nice
for coming.
You.
What do you, I mean, maybe this is asking too much for a conclusion, but suppose you were trying to define this TTbar deformed theory directly at the limit, as opposed to being the limit of the UV flow of a ordinary quantum field theory. Like what objects would you try to define it in terms of? You know, ordinary field theories, we have correlation functions, or partition functions on different geometries. What would make sense? On the other hand, we know in string theory there aren't very many things that you can compute precisely.
Yeah, well, okay. This is a very good question. It's exactly at the heart of the matter. Let me first mention one. Excuse me for pointing out obvious. There is a way, and actually that's what I used. The way to define it in terms of the scattering matrix.
Right.
All right. After all, what we are having here is this matrix, which looks like it looks at in all respects as a decent and a consistent S matrix, which satisfy all the properties which theoretical physicists could dream of. But nonetheless, the calculation shows that there is no conventional local structure behind it. So your question basically, I understand your question is you would like to know what replaces
good. That's
the conventional local structure.
Yeah, that's a good question. That's probably a better question than I asked, but yes.
Again, this is a good question. That means I don't know how to answer it, but nonetheless, let me say this: simply dismissing the local structure, saying that there is none, right, would be kind of a little bit too. I don't know. I think some part of the local structure persists. At least the whole activity, the whole basis of the deformation, of the construction of the deformation, is based on the local energy momentum tensor. So at least, and that's conventional part of the local structure. So that part must be there. And some parts of the operator product expansions involving at least this deforming operators could persist. On the other hand, if you try to extend the conventional local structure, then you immediately come into problems. There is even a problem in the if you look at the correlation functions, for instance, right? You could ask how they behave, and there are reasons to believe that there are singularities which are not admissible by conventional local structure, but the situation might be even worse. For instance, if I something which let me put it this way: given this matrix, you could try to reconstruct the local operators and correlation functions, right? And the problem which you encounter is that in many cases, not the decomposition, the spectral expansion, not only doesn't converge, but doesn't exist.
Okay.
Meaning that if you try to take something which pretends to be local operators and attempt to write down intermediate state decomposition, the sum over the states diverge badly at high energies. So basically, the intermediate state decomposition doesn't define the function even in the sense of analytic continuation. No, but short way to answer that is that that's generally open question. I don't know. I think it's the most intriguing part here.
I mean, a much more tentative or timid thing. We know from our experience in string theory that, roughly speaking, a souped up kind of S matrix is to put the theory on anti-de Sitter space and consider correlators at the boundary.
Yes.
I don't know, could you try to put this TTbar theory on ADS2 and look at the one-dimensional boundary? Will it have simple correlators?
That part I don't know, but of course, I mean, of course, there is a conjectured interpretation of the conjectured relation of the TTbar deformation with the bulk properties of the gravitational dual.
Yeah.
I don't know what to say. It looks very tantalizing, but again there are too many questions which I don't know how to answer here. But let me put it a little bit differently. So you're right in saying that we already know this. Of course we know a lot about this situation about the string theories, where of course there is a known difficulties with local structure and so forth. But it's so it's tempting to say that we have basically in order to fill the space which geometry I want to understand, you basically take field theories and add the string theories, or consider field theories as a limit of string theories, and that's all. We have basically strings and everything derivable from that. But I think that this TTbar deformation stuff, or maybe I'm kidding myself, but it looks like there is a lot more. So the TTbar deformed, they seem to share something with the string theories, but they don't look to be just versions of string theories. I'm not insisting on that, but at least at the moment I cannot see how that TTbar deformations with all this Hagedorn behavior and all are reducible to strings.
Very, very interesting. Thanks very much. I'll let somebody else have at it.
Maybe I'll ask a question. So you used several times during the talk, you mentioned operator product expansion, which is something we understand very well, what it means and how it converges, for conformal field theories. But even in situations like, never mind the TTbar deformation, just a massive quantum field theory, what do you think is true about properties of operator product expansion? Does it converge in a finite radius, or it's asymptotic, or what is?
Well, in conventional quantum field theory, I think the situation is not. It's not much of it is proven, but many examples suggest that. Well, first of all, the situation is likely different in two-dimensional and higher dimensional quantum field theories. And what I'm going to say, or it might be different, but at least I can sort of I can make some statements or suggest some statements about two-dimensional situation. And in this case, I think it's relatively safe to say that the operator product expansion has, in massive theory, have more or less the same property of convergence as in conformal field theory, meaning that it converges in some domain of R, depending on which correlation function you are considering. But what's more important is that it's very likely that the operator product coefficients, you can choose a basis in such a way that the operator product coefficients have the same analyticity as the same, more or less the same analytic properties as the conformal field theory, meaning that if you take well, basically it's analytic on the universal cover of the of the plane with the light cone taken out. But I'm not sure I'm answering your question.
No, yeah, I guess this is more or less what I was asking, because it is not proven, right? It is sort of an open.
Oh no, it's not proven. It's not proven. It's but there are many examples where you could at least make some probe, and well, of course there are some solvable things like Pinlev-Ecker relation functions, Ising model, and so forth, which sort of support that. And generally, it seems to be consistent. But I think part of your remark was that all this business with TTbar, it's a peculiar in the sense that result sort of suggests that breakdown of the local structure, but nonetheless, some part of local structure, like operator product expansion, like you mentioned, are needed in order to justify this. So it's like making assumption which is not supported by the result.
Yes, I agree.
Well, on the subject of local structure that does or doesn't survive, I mean, one that's closely related to the stress energy tensor are, attempts to compute entanglement entropies and so on. Do you have opinions about that?
Not specifically. Yeah, I mean that's important part, but I think I'm lost at much more elementary level. For example, I mean, without local structure, it's not really easy to define a Hamiltonian. So we assume that this theory has a Hamiltonian, but how it relates to? Yes, I mean, I don't know what to say here.
So yeah, you say you have the stress energy levels, but not the operator.
Well, I mean, we have the energy levels, which in some sense define the operator, but it's very questionable if we can write this operator as an integral of local density. So it's I don't know. It's if the theory exists, it misses the basics.
Can you say a little bit more about the instability of the vacuum that you mentioned? And I guess in your conventions it was alpha positive.
Mm-hmm. It's I didn't discuss this, but in the this can be analyzed in the context of semi-classical approximation when you consider a limit of large central charge. You take a deformed conformal field theory and take a limit of large central charge, and then it's possible to construct some sort of effective action, effective action for the deformed theory, and it turns out that in the case of wrong sign of the positive sign of alpha, it's sufficiently small r. The effective action doesn't have any bottom. So depending on the value of R, it's either bounded from below or not. So basically, for small r, it becomes unbounded from below. What is strange about it is that usually in such situation, first of all, the close to the situation where the stability is lost, there are large fluctuations which would normally transform the simple. So in this semi-classical approximation, this square root is just a simple mean field singularity, right? Related to the loss of stability at certain point. Now, generally, you would expect that away from the classical limit, the fluctuations would convert the singularity from the square root to something more complicated, because close to the threshold of stability, there is a class of fluctuations which grow and produce a complicated singularity, which doesn't happen, and that's very strange. So what I know is the result in the leading classical approximation, where that's what happens. But in order to understand why singularity remains of this boring type, some sort of analysis of fluctuations is needed. Just like I said, I still don't know how to do that.
Okay. Anybody else? Going once. Okay. Well, let me just say thank you again for this really interesting review. Yeah, we can discuss other questions offline. Once again, anybody else who wants to ask, now is the time. Okay, then let's thank Sasha again for a beautiful talk.
Thank you.
And take care, everyone.
All right, thanks again.
Sasha, it was great seeing you. I'll sign off. I hope we see each other in real life.